All this time, we have seen that after each sublayer, there is an additional layer for a skip connection and layer normalization. We have not forgotten about it. After each sublayer, that is, after the attention module and after the feed-forward networks, we have some intermediate steps. We have a skip connection and a layer normalization. In this diagram, we can see where these skip connections and layer normalizations are applied. Let's remember the definitions of residual connection and layer normalization. The residual connection, also called skip connection, adds the input of a layer directly to its output. The layer normalization helps normalize the outputs of the layer across all its features. The residual connection is important because it helps mitigate vanishing gradients, and also it can act as an identity shortcut, allowing the model to bypass one or more layers. At the end, it helps in training deeper networks by ensuring that the addition of layers does not degrade performance. Remember that we are not only passing through an attention layer and a feed-forward layer, but we are repeating this for each layer of the encoder or the decoder, so the role of the residual connection is really important. Now, in a recent paper from probably last week, I found a new approach to the design of the transformer where they are removing the skip connections, the layer normalizations, and other layers. That is called the simplistic transformer. I recommend that you look for that and read it. Very interesting reading. The layer normalization is important because it ensures that the outputs of a layer have a consistent scale. This helps in the training process and in getting convergence faster. Let's review again the entire process and roles of these two operations in the case of the encoder. In the case of the residual connection, when the encoder processes an input token, it first goes through the self-attention mechanism where it interacts with other tokens. The output of this self-attention, added to the original input token, meaning the residual connection, then goes through the feed-forward neural network. This process ensures that the network doesn't lose vital information from the original input even as it goes deeper. In the case of the layer normalization, after each one of these steps, meaning the post self-attention and post the FFNN, layer normalization is applied. This step is like recalibrating the data, ensuring that the output of each layer maintains a standard scale. It helps the model in adapting to different input distributions and accelerates the training process. So, in summary, residual connections allow for easier gradient flow and training of deep networks, while layer normalization standardizes the output of each layer, promoting faster and more stable training. How are these layers implemented in code? Let's see it. I will show you here the generic PyTorch layer norm and also a custom layer norm. The built-in PyTorch layer normalization module automatically includes both a weight and a bias that are learned during training. In this custom layer norm function that I am showing you here, it behaves very similar to the built-in layer normalization of PyTorch, but with one key difference. In this case, it allows you to optionally include the bias term. When initializing the custom layer normalization, you can set bias to false and it will not use a bias in its calculation. This will provide flexibility in cases where you want to experiment with a model that doesn't include a bias term for normalization.